Hello, everyone. So hello, and thank you for joining another lecture. We're going to talk about triangular meshes today. All right, so triangular meshes. Why are we talking about triangular meshes? Because GPUs are triangular mesh rendering machines. I mean, you can think that you could render all sorts of different things on the GPU, but no, not really. You just render triangles. GPUs have, actually, the graphics API has a number of primitives. Like there are like points. We've been using points for our previous project, right? There are lines, line segments more specifically, but they're called lines. We used to have quads, now we have patches. But everything in the end, right before they reach the rasterizer, they turn into a bunch of triangles. So when in your previous project, you've been rendering points, right? You thought you were rendering points, you were actually rendering triangles under the hood without knowing. You were sending points, but those points were converted to a bunch of triangles. So how do you convert a point to a triangle? Well, you give it a size, and you get basically a camera-facing quad, and that quad is split into two triangles. And that's how rasterizer pretty much handles it, right? I mean, there could be other optimizations for some GPUs, but that's pretty much the gist of it. So we're dealing with triangle rendering machines. So that's why triangular meshes are very, very important. And as we talked about this in the Introduction to Computer Graphics course, most models that we use in computer graphics are in the end either initially represented or in the end converted to triangular meshes before we render them. Right? So when we're trying to render something, we're basically dealing with a bunch of triangular meshes. All right, so let's start with that. So we're going to talk about how we handle triangles and stuff today. All right. So what's a triangle? A triangle is defined by vertices, right? These three vertices, and by moving those vertices in space, we sort of define where the triangle is. So like these three vertices will define a triangle like this, right? And we color it, and there you go, there's your triangle. Now, when you're dealing with these triangles and triangular meshes, one of the most important operations that we're going to have to do is to interpolate data between these vertices. And actually, our GPU is going to help with a lot of triangle rendering related stuff that is included. Yeah. So I have this triangle. So the operation that I'm going to do when I'm rendering this triangle is that I'm going to be sending these vertices through my vertex shader, and then they'll pass through the fragment, pass through the rasterizer, and then I'm going to get some fragments, right, in the fragment shader. More specifically, in the fragment shader, I'm going to get a particular point on this triangle, just one point on this triangle. Like let's say this point, I pick this point, I'm going to get some point. Let's call it P. So what the GPU is going to do for me is that it's going to compute that position P. I never provide that position P specifically. I just provide these vertex positions in the canonical view volume, right? P0, P1, P2. I provide these vertex positions in whatever space I want, and then in my vertex shader, I convert them to positions in the canonical view volume. And in my fragment shader, I can actually get this position if I want to use that position, that position in the canonical view volume that's generated by interpolating these three input positions. Right? So what is that interpolation? It looks like something like this. You guys might be familiar with this interpolation. What is this? It's basically interpolation using barycentric coordinates. So the barycentric coordinates of this point P in the middle of the triangle can be represented by these three scalar values. So it's like a 3D vector. So this is a very, very important concept. And if you're writing a software rasterizer, or software renderer, you're going to have to deal with this yourself. But nice thing is that GPU can handle a lot of the rendering operations for us, rasterization-based rendering operations for us, and it will handle these barycentric coordinates sort of automatically. So when the rasterizer is generating some fragments and sending some points like this one to our fragment shader, it's going to compute these barycentric coordinates, and it's going to do this sort of interpolation. So just so that we refresh our memory about barycentric coordinates, so these three scalar values that form the barycentric coordinates, their property is that they add up to 1. And the fact that they add up to 1 does not mean that this point is on this triangle. Actually, any point on the plane defined by these 3 points in space, any point on that plane will have this property. When you compute the barycentric coordinates, they will add up to 1. If they don't add up to 1, if you use some interpolation such that these 3 scalar values don't add up to 1, then this point that you're going to get will be outside of that plane. If you want a point that's on the plane defined by these 3 vertices, these 3 input vertices, then the barycentric coordinates must add up to 1, right? But if you want a point that's going to be inside the triangle, there is going to be some additional constraints that these barycentric coordinates they're not only adding up to 1, but also each one of them individually will be between 0 and 1. So none of them will be greater than 1, and none of them will be less than 0. If that happens, then you're representing a point that's outside of the triangle. But this is not the sort of stuff that we're going to need to worry about when we're rendering on the GPU, because the GPU will do all this barycentric interpolation stuff for us. So it's going to compute the barycentric coordinates, it's going to do all this interpolation. In fact, anything that we send through our vertex shader, any data that we send per vertex, is going to arrive at our fragment shader as an interpolated value. For example, if we send positions, which we must, right? We send those canonical view volume positions to our rasterizer. Our rasterizer will have this interpolated canonical view volume position. So if we don't use it in our fragment shader, we're not going to see it. But if we want to see it, we can actually access it in the fragment shader. But it's not just specific to the positions, anything that you send. For example, I can send per vertex color values. Like I pick 3 color values, is red, green, blue, and my rasterizer is going to just interpolate these color values using exactly this formula, the very same alpha, beta, and gamma coordinates, the very same barycentric coordinates, and it's going to do this interpolation exactly using a function that looks very much like this to compute the interpolated color at that position. Right? It's going to do the same interpolation for red, green, and blue color components independently, and you'll have a interpolated color in the middle here somewhere. Right? So that's how GPU rendering works. So you just need to understand that this is what's happening under the hood, but this is not something you're going to have to implement yourselves, because GPU will do this interpolation for you. But you just need to understand that this interpolation is going to happen. Right? So again, looking at our GPU pipeline, we're sending a bunch of triangles, and those triangles are arriving our vertex shaders as one vertex at a time. And then we transform those vertices, a rasterizer gets it, and the rasterizer generates these fragments. Right? So these fragments of our triangle. More specifically, the rasterizer will generate the fragments, and it will interpolate the data at the centers of these pixel positions. So the positions on the triangle that correspond to the centers of the pixels is the data that we're going to get at our fragment shaders. Actually, in the normal rasterization mode, only the pixels where the center of the pixel is inside a triangle will have a fragment. So these fragments are generated only for pixels that where the center of the fragment is inside the triangle. Well, that's conceptually true, not exactly accurate, because there are some operations going on the GPU. Like one of the things that we would like to do is we would like to sometimes compute the screen space derivatives. Like, why would we need that? Well, we would need that for a lot of operations. For example, texture mapping is one of them. We're going to talk about texture mapping extensively, and you'll see why we need screen space derivatives. And if that term screen space derivative sounds a little frightening to you, it's not a frightening term at all. It's basically the difference of interpolated values between neighboring pixels. That's what it means. And so that's the finite difference, more specifically, finite difference way of computing those derivatives. And that's exactly what the GPUs will do. So I would like to know, for a lot of the interpolated values, I would like to know how much those values change on the screen as I move from one pixel to the neighboring pixel. Right? I would like to know that for a lot of operations. Texture mapping is one of them. There are other examples that I don't want to get into. But I just want to iterate one thing here, is that GPUs will not only do this interpolation for us, not only interpolate those values, GPUs will also compute the screen space derivatives of any value that we want. So if I want to know how much this color value is changing as I go from one pixel to the next, GPU will compute that for me as well. And to be able to compute that, GPUs will not only generate these fragments that will actually show up in the final rendered image, it will also show some fragments that will be outside of this, triangle, so that it can compute the interpolated values outside of the triangle, possibly, so that it can compute these screen space derivatives. So what ends up happening is that the rasterizer here will generate 2 by 2 fragments, 2 by 2 pixel fragments. So there's going to be a 2 by 2 group, another 2 by 2, another 2 by 2. So if there's a fragment in here inside a 2 by 2 group, that entire 2 by 2 group will appear as a fragment. And whether or not our fragment shader is called for each and every one of those, that's another question. But at least those fragments are generated. So this is a little bit of a simplified picture is what I'm trying to say. But because this is an interactive computer graphics course and we're sort of talking about the details of how GPUs operate, I kind of felt compelled to explain that detail that we don't necessarily need to know to program GPUs. So you can, for all practical purposes, assume that all you're getting are these fragments, even though GPU might actually generate a few other fragments that will not show up in the final rendered image. Okay? Is that enough complexity for this simple, super simple thing? Yeah, okay. All right, so our GPU is generating this stuff. Now let's take a look at how this works. Now, whatever data you send from your vertex shader to your fragment shader is going to be interpolated. We're just saying out. We're just saying out vector 4, and over here it's going to be in vector 4 vColor, right? Whatever output you have in your vertex shader is going to arrive in your fragment shader as an interpolated value, right? So that's the concept. All right, let's go back to triangular meshes. In the previous project, we've loaded an OBJ file, and the OBJ file can be used for representing all sorts of objects, model formats, but they're probably more frequently used for representing triangular meshes because, say, we use triangular meshes for representing almost everything, right? So there are lots of different formats for representing triangular meshes. There isn't just one format. There isn't just one file format. There isn't just one structure type. There are a whole bunch of ways of representing triangular meshes, but this is the structure that fits well in the way that our GPUs handle triangular meshes. And the OBJ file format sort of follows that structure, and that's why I'm sort of talking about this. Now we have loaded an OBJ file for our project, but we didn't quite use the OBJ file so much, right? We just loaded its data and we got a list of vertices and we were just drawing them as points, right? So that's what we did for our last project. In our new project, we'll actually be rendering triangular meshes. A typical way of representing representing triangular meshes, which is exactly how the OBJ file format represents triangular meshes, is having a list of vertices and a list of triangles. So if I'm having a list of triangles, why am I having a list of vertices? Like, I could just be representing a list of triangles, right? A triangle at 3 positions, I just place those 3 positions, then I move to the next triangle. I can do that, but that would be a little bit too expensive. And the reason for that is, on a triangular mesh surface, vertices are shared by neighboring triangles. Actually, on average, a vertex would be shared by about 6 triangles. So 6 triangles on average would use a particular vertex. So if I don't have a list of vertices, but I just store a list of triangles that contain all the information that I need per triangle, then I will be duplicating the same data 6 times on average. Instead, what this structure would do is they will store a list of vertices with vertex positions, more specifically, and then a list of vertex indices per triangle. So each triangle will just have 3 indices, whatever they are, 0, 1, 2, and that would be indices to these vertices. Now I'm going to talk about the OBJ file format a little bit in this context, but it differs from the way that OpenGL and the GPUs handle the vertex indices and triangles a little bit. So I'll talk about that detail, which is going to be relevant for our upcoming project. Now, we're going to have a list of vertices. They're going to be the positions, and we're going to have indices per triangle to the list of vertices to define the positions. So you can think of these positions as vertex attributes, obviously. So going back to OpenGL, so this is what you did, right? Right, last time in the previous project, you just generated a vertex buffer object for our one vertex attribute, which was the positions, right? So this is what we had, and we rendered them using GL points, and that was it. Of course, we can have more than one attribute. For example, like positions, we can have colors. So here's another vertex buffer object, let's say. It's containing the list of colors. All right. So let's remove this complexity for the time being. Let's concentrate on this. So I have a bunch of positions. Now, if I were to render these as points, each one of them would be a point in space, and I would send them through the vertex shader, and they will have a position in the canonical view volume, and my GPU will generate the fragments for those points. So I'll have a bunch of points, just like we did. If we want to have triangles, we're going to have to figure out a way to form triangles from them. The simplest way, the easiest way we can do is to say that, you know what, each 3 consecutive vertex will form a triangle. So I have 3 vertices here. These 3 vertices will form a triangle like this. All right? And then I'll move to the next 3 vertices, and that would form another triangle in space. And I can render them just like we rendered points using the same call with GL draw arrays, but instead of saying GL points, I'm just saying GL triangles. But this means specifically that each 3 vertices here will form a triangle. Again, I put 6 here because 6 is the number of vertices I have. So starting from the beginning of my vertex array, I'm going to draw 6 vertices, and each 3 will form a triangle. Simple enough? All right. So in this case, I just color-coded them to show you which one corresponds to which one. Well, what's happening here? Actually, it turns out that these 2 triangles that I've been trying to draw here were a quad. Can you see that? Like, if you combine these 2 triangles together, they would form a quad, right? So like this red one is the same red one here, this blue one is the same blue one here. And I color coded them. So what happened here is that, I'm not using any vertex indices and that complexity. I'm just drawing them like this, which is fine, but I sort of duplicated my data. You see that? Like this red vertex is appearing twice. Same goes for the blue one. It's appearing over here and then down here. So I basically duplicated my data. I duplicated my storage, which was sort of unnecessary. So can I avoid that? Actually, I could. No, because I actually have here just 4 vertices, but I've allocated enough space for 6. Now, this may not sound too bad to you. Okay, I mean like 50% extra overhead, not that big a deal. But this is just 2 triangles. If I have a surface, I'm telling you, on average, each vertex will get duplicated about 6 times, which is significant, right? Like 6 times. So you would be allocating 6 times more memory. That would be bad. But in this case, it's just 50% because only 2 of the vertices are duplicated. Okay, so if I were to just store the vertices that I actually have in my data, that will be just these 4 vertices, right? So going back to our notion of representing our triangles as elements, I could say, hey, I have these elements. Each element is representing a triangle. So in this case, the first element has indices 0, 1, and 2. That means 0, 1, and 2. And that would form this triangle, right? And the next one will form this triangle using indices 0, 2, 3. If I have an additional array like this, like the elements array as we call it in the graphics API, OpenGL specifically, I sort of eliminated this extra storage for vertices that I really didn't need. So I'm storing my vertex attributes only once, but then I need to store this element array that will tell me how the triangles are formed out of these vertices, right? And once we have that, instead of using GL triangles like this, GL draw arrays with triangles, this is not going to work because I haven't duplicated bin data. So nope, this is not working out. I'm going to be using a different call that's going to look like this. Whoa, there's no space for me here. So this is called GL draw elements, right? And it's drawing triangles. And I'm going to be using 6 vertices. Each one of them are stored as unsigned integers, and I'm starting from the very beginning. All right, so that's what this call means. So GL draw elements basically is what we're going to be using. Now, to be able to use this, we need to generate this element array, this element buffer. So let's talk about how we could do that. So an element buffer data could look like something like this. Like I have unsigned integers, 0, 1, 2, or 0, 2, 3. Obviously, I mean, these are very small values, right? I don't need a full 32-bit unsigned integer to represent them. I could actually be using, a lot fewer bits. And the graphics API will allow me to do that. So if you're thinking that, oh, there's wasted storage here, too much. Yes, there is. And you can avoid that. For example, you could store unsigned characters, right? So that it just bytes per element. That's fine too. But let's keep things general. All right, so let's assume that this could have been a much larger mesh with a lot more triangles. So let's say that this is my element array. Now, as you can see, this is the standard format that I've been using. So this kind of looks like a 2D array, but it isn't. It's just a 1D array, right? I'm just writing it in this format so I can see it better. Other than that, it's just a 1D array of 6 elements and nothing else. Right? So 0, 1, 2, 0, 2, 3, they're defining my vertex indices. Now I need to generate a buffer. More specifically, it's going to be an element buffer that's going to contain this data. And then I'm going to tell OpenGL that I want to use this buffer, and I'm going to render using that. And here's how I can do it. There it is. So this element buffer, I called it eBuffer, and I could call it whatever. And if you pay attention here, I'm using exactly the same function call that I used for the vertex buffer object. So when I generate this buffer, I haven't said anything about this being an element buffer or just a vertex buffer. It's just a buffer, right? So it's generated buffer. What differs is over here. I'm binding this buffer as an element array buffer. Right? This is where I define, oh yeah, this is going to be an element array. So I bind this to the element array. Now, in a vertex array object, remember vertex array objects? They're containing all the, like how buffers are connected to different attributes. It was storing all that information. In a vertex array object, there exists just one single element array buffer that can be active at any given time. We can have multiple vertex buffer objects that contain the vertex data, but element arrays, I'm going to have only one. So I can create multiple, but at any time, only one of them is going to be active, and only one of them is going to be used. So I created this, and I bind this, and I'm setting its data just like setting the data for a vertex buffer object. There isn't really anything different here, right? So this is the initialization part, all this stuff. And when I'm ready to render, I'm going to, of course, bind the buffer. Of course, I could do this binding as a part of the initialization, and I store it in my vertex array object, and that will remember all the details and like how everything is connected. And then I just need to call GL draw elements, and I'm done. So we're going to have array buffers for storing the vertex data, per vertex data, the vertex attributes like vertex positions and color and surface normals and whatever else we want to send per vertex. That's going to be in vertex array buffer, right? So GL array buffer. So GL element array buffer is a very specific type of buffer that's going to contain the elements. And we're going to be using that for rendering. So we can have, when we're rendering, we can have multiple vertex attributes. That means we can have multiple vertex buffer objects attached to different attributes. But we're going to have only a single element array buffer. So I can't say, because it doesn't make any sense. Like, I can't get indices from multiple different buffers and combine them somehow. I mean, a triangle is formed by 3 vertices. I just need 3 vertex indices. I can't get 3 vertex indices and combine them from 2 different buffers. That doesn't work like that. Although I think this is a good place to talk about this. It could work like that. And that's exactly how the OBJ file works. So, for example, I have a list of vertex attributes. Right? I have a list of vertex attributes. That's vertex positions. Now I can have another vertex buffer object that could contain a different vertex attribute. Let's say vertex color. So when I'm using these elements, when I say get vertex 0 for, like, let's say my vertex element is forming a triangle using vertices 0, 1, 2, like just first 3. Okay? So it's going to be index 0, 1, 2 for this vertex buffer object. If I have another vertex buffer object containing vertex colors, it's going to be the first 3 elements of that buffer object. And if I have another one, that's going to be the first 3 of that vertex buffer object as well. So the indices 0, 1, 2 that define my triangle is going to be the same indices into any one of my vertex buffer objects that I'm using for my vertex attributes. Okay? So I can just say, you know what, for positions get 0, 1, 2, but then for color get 3, 5, 7. I can't do that. Graphics API will not allow that because that's how it's designed. So I'm going to have to use the same exact indices. Now here's the tricky bit. Here's the bit that's going to hurt you for the upcoming project if you don't pay attention. That is not the case for the OBJ file format. The OBJ file format will allow you to form a triangle using different indices for different attributes. For example, for vertex positions, a triangle can have indices 0, 1, 2, and then for example, for surface normals, they are also defined per vertex. It can have different indices. A triangle can have different indices, saying 2, 5, 7, whatever. So an OBJ file will allow you to specify different sets of indices for different attributes. We cannot have that in the graphics API. Unfortunately, the graphics API will not allow us to do this because GPUs are not designed to handle that. Right? So it's not a limitation that's specific to OpenGL, just to be clear. That's how GPUs are designed to render, and that's why the graphics API does not support it. So if GPUs could handle different sets of indices for different attributes, then the graphics API would have that functionality. But it doesn't have that functionality because GPUs don't support it. Okay, and that's going to be an important distinction. It's going to be an important distinction because the input to the code that we will be writing will be an OBJ file, which does support this extra complexity. Then OBJ file can have different sets of indices for each one of these attributes. More specifically, in our upcoming project, we're going to have vertex attributes representing positions, and we're going to have another set of vertex attributes representing vertex normals, surface normals. We're going to talk about why we need surface normals and how we use them next time. But we're going to have those attributes, and OBJ file, I'm repeating again, will have two separate sets of indices. And if you assume that they are going to be the same indices, you may be in trouble. Right? They don't have to be the same set of indices. In an OBJ file, they can be very different indices for different attributes. So because of that, because OBJ file supports that, the code in my code base, the triangle mesh class, also supports that. So when it's parsing an OBJ file and loading it, it's loading separate indices for vertex positions and a separate set of indices for surface normals and a separate set of indices for texture coordinates, another attribute. So for each triangle, we're going to have 3 sets of indices, because that's what OBJ file supports. But OpenGL does not support it, because GPU does not support it. So what do? We kind of need to figure out a way to represent everything using a single set of indices. Okay? And that's going to be a little bit of a tricky thing to do. And I have not included code for you to do that. So as lovely as it is that we have an element array, and we can use these elements arrays, and by using this element array, I can have this more compact form. I'm just having a list of vertices and elements, and I'm generating this lovely element buffer using this, and then I don't have to take this vertex position attributes and duplicate them. I don't have to do that, which is great. But then I kind of need to make sure that I have those indices. Right, so I need to make sure that, let me go back. Now these indices that I'm using are going to be the same indices for all of my vertex attributes, which is not necessarily the case. Yeah, for the OBJ file, they're going to be different. So what do you do? What do you do? Well, what you can do is that you can just, instead of just assuming that whatever indices OBJ file has for positions, they're going to be the same indices for normals. They can be, but they don't have to be. Instead of just assuming that, you could just process this data structure, and if I have a triangle that's using 2 different indices for surface normal and vertex position, I can just duplicate that vertex. So if I have a vertex that has a particular attribute, And if the same vertex is getting a different attribute for a different triangle, I need to duplicate that vertex. I'm going to have two copies of that vertex, right? Because I cannot have positions together with different attributes. So all of these vertex attributes for a vertex is going to form one vertex. And if I need to change one of the attributes for the vertex, I need to have a full copy of that entire vertex for all of the attributes. Right? That's very important. So if you just blindly take whatever we have in that triangle mesh class and assume that those indices will be fine and generate your element buffer and then try to render, you're going to be in trouble in some places. You're going to say, I'm saying in some places because some OBJ files, by luck, can have the same indices for all the attributes. You could be lucky, and it is the case sometimes. And if you're lucky, it's just your code is going to work, and then you're going to load another OBJ file, and it's going to look weird because all these indices will be wrong for some attributes. They'll be right for some attributes. They'll be wrong for some other attributes, and things will look just as weird. What kind of weird? Yeah, but your vertex attribute is not the right attribute. So, what you're going to render is going to be rendered using the wrong attributes. So you'll get whatever that produces. I would like you to sort of understand and appreciate this complexity. So if you would like to use vertex element buffers for rendering your triangular meshes, I would recommend it. I would absolutely recommend it, but you need to understand that you may have to do a bit more work than just this, okay? Because the input to your software is not going to have this uniform sets of indices. So you kind of need to process your mesh data and figure out which vertices you'll need to duplicate if you need to duplicate any vertices. So that's it's definitely possible. It's not too hard to implement, but it's not perfectly trivial. So if you don't want to deal with that complexity, I would say don't use element buffers. But I need you to understand that this is a lot more efficient than duplicating all of your vertices. So what do we do? What do we do? Like, we have two options here, as you can see. I can either process my mesh and make sure that these indices that I'm using are going to be exactly the same indices for all of my vertex attributes, right? I'll need to process my mesh and make sure that it is the same. And if I need to duplicate some vertices, I'm going to duplicate some vertices and change the indices of some triangles and, process the mesh data structure such that those indices are the same indices for all of the attributes. And then I can use this, which is going to be great, which is going to be the efficient way of rendering this. Or I'm going to use GL draw arrays, and I'm not going to do any element buffer stuff. If I use GL draw arrays, well, I'm going to have to process that as well, but that processing is a little bit easier. I can just go over my triangle list, and for each triangle, I find which vertex attributes it's using, and I copy all of them to all of my arrays. Basically, I'm going to be duplicating that data as many times as I need, and in the end, if I'm just drawing, for example, in this case, if I'm drawing just two triangles, I will end up with an array that's going to contain 6 vertices. But that processing is a lot easier. You just put a for loop and go over each one of your triangles, generate all that data, duplicate all of the vertices, and then you don't need to look back. You just you don't need to have an element array. You just say, oh, each consecutive 3 vertices will form a triangle. Right? So you need to choose. You can do this. That means more efficient way of doing rendering, but a bit more work in the way that you're going to be processing the triangle data. Or you can do this easier processing. Again, there's going to be some processing. You can't just send the vertex buffer object that you generated from this and say, oh, render triangles. That's not going to work. If you just try to draw triangles out of this, because these three consecutive vertices may form a triangle, or maybe they belong to completely different triangles. Who knows, right? So you can't just treat it like that. So you kind of need to generate your own array and then send that as your vertex buffer object for each one of the attributes that we will need. So as I said, you have these two options. One of them is easier to implement, but less efficient. The other one is harder to implement, but more efficient. And for the upcoming project, that's going to be your choice. You can do whatever you want, whichever one you want. Well, you say, is this the most efficient way of rendering? It's like this, let's go back, this element buffer stuff. Is this the most efficient way of rendering triangles? No. We can do better. So we're gonna do a trick. We're gonna do triangle strips. So here's how that's going to work. So this was my vertex buffer object, let's say. You know what I'm going to do? I'm going to do a little bit of a pre-processing here. I'm going to swap the order of these two vertices. All right, I'm doing this pre-processing. Okay, I swapped the order. Why did I do that? Because if I do this, I can render the two triangles like so. The first vertex is this green vertex, right? The second vertex is this one, and the third vertex is the blue over here. So I could say these three vertices form the triangle. I formed my first triangle. So this is very much like GL triangles now. Now I have one vertex left here, and that one vertex is the remaining vertex here. But I ordered my vertices such that, now pay attention here, now such that these next three vertices would form the next triangle. So if I order my vertex attributes such that every time I add another vertex, I form another valid triangle that I want to draw, I form more specifically, I form a triangle strip. I can render it that way, and I can just say, call this GL draw arrays triangle strip. And I only have four vertices, but four vertices as triangle strip would be two triangles. All right, so 4 here means 2 triangles. If I had 3 triangles, this would be 5. So the way it goes for a strip is that, you have the first vertex and the second vertex. As soon as I have the third vertex, that's when I form a triangle. So again, so this was the first, this is the second, and this is the third, and they form the triangle. So these are my last 2 vertices. And the next vertex I add will form a triangle with the last 2 vertices. Now these are the last 2 vertices, and the next vertex I add will form a triangle with that, and the next vertex I add will form another triangle, and the next one will form another triangle, the next one will form another triangle, and this way I can draw my object. Now this is, as you can see, more efficient than just using indices, because every single vertex here, every vertex I add is forming a new triangle, which is a lot more efficient than just looking at 3 vertices. All right? So this is probably the most efficient way of rendering stuff. So, in games and interactive graphics applications that try to optimize this triangle drawing stuff as much as possible, they will use triangle strips. But this is still not quite perfect, because it might be possible that for an entire object, you might be able to form a single strip that goes over the entire object and draws it. But even if you do so, this is one strip. If I have the part of the surface that's right above here, the strip will go around and come back here, and these vertices will appear again, right, forming the triangles up here. So if you just color the different strips on an object, here's an example. This is just showing the different strips generated on this object colored with a different color. So I have different strips here, and each strip is drawn, in this case, very efficiently. Nonetheless, as you can see, the vertices between 2 strips are shared by those 2 strips. So I am going to be processing those vertices twice, not just one time. I mean, it's a lot better than processing the same vertex 6 times, right? I'm processing them on average twice now, which is a lot better, but it's not going to be just once. Now, this is going to be the most efficient way of handling this. This is going to be the most efficient way of rendering triangles. But this requires you to generate these strips. So you get your triangle mesh data, and then you're going to need to form these strips out of the triangle mesh data. Ideally, you would like to have one continuous strip that draws the entire object. And we can do that. We can do that, although it's a little... you know what? Let me actually show you this. I wasn't planning to show you this, but we have a little bit of time. So let me see if I can do that. So if I turn off the light here. All right. You can see the board behind me, right? Good. All right. You know what? Let's get rid of the slides. Let's get rid of the slides. Okay. So if I have 2 strips, I have a triangle strip that goes like this. And then let's say it ended here at this vertex. Now I have another triangle strip that starts here. All right, so it starts with this vertex. So my one strip ended at this vertex, and my next strip will start at this vertex. Now, if I just say that, oh, these were the last two, so these were the last 2 vertices when I was drawing. If I just add this vertex, it's not going to be very nice because I'll be forming a triangle like this. Right? If I just add this vertex next, it forms a triangle like this, which does not exist in my data. I don't want this triangle. Okay? That triangle I do not want. So what do? I do a little bit of a trick. Okay? I duplicate this vertex. I put this vertex again on the list. So if I add this vertex again, my last 3 vertices are this one, and this one again. So I formed a triangle that is a line. I formed a triangle with no area. So I send it to my rasterizer. The rasterizer will generate absolutely 0 fragments from this. Right? So it's perfectly safe. I mean, I send it to my rasterizer, yes, but my rasterizer is not outputting anything for this. So it's done. All right. So now my last 2 vertices are this vertex. Right? So if I add this vertex, now I'm going to be forming a triangle that's going to be a line. Because these 2 vertices and then this one, that's going to be a line. Right? So that's not going to generate any fragments either. That's going to disappear. And then I duplicate this vertex again. Now my last 3 vertices are this one, and this one again. Again, I have a degenerate triangle that's going to form just a line segment. Again, it's not going to produce any fragments. Nothing is going to be visible. And I ended up here. Right? My next vertex in this case is going to be this one. And that's going to form a line segment here because I have this vertex twice and this vertex forming a triangle. Again, it's not going to generate anything. But finally, my last 2 vertices are these 2. So finally, I can just put this vertex and get my next triangle. Okay? So this way, I can go from one strip to another strip and continue drawing. Now, why would I want to do that? Why would I want to do that? Well, I would like to do that because even though I can draw these strips separately, one strip after another strip after another strip, I can do that. That is not very efficient. Because every time I draw a new strip, my graphics pipeline will reset and I'll start again. Every time you say GL draw arrays or GL draw elements, there's a little bit of a cost to it. Okay? And if I have to do that, let's say for drawing something like this, if I have to do that on the order of 100 times, I'm paying that cost of initiating rendering 100 times. But if I were to do this with only one strip, so I treat all of these strips as if it's just I connect them just using the trick that I just told you, then this whole thing, I can treat it as a single strip, even though it isn't. I can draw it as if it's a single strip, and then you can draw it using just one GL draw arrays or GL draw elements call. Right? So that's going to make the drawing process quite a bit more efficient. That's why I would like to do that. Now, an obvious question, I think, at this point is, I could use GL draw arrays for drawing these strips. I could also do triangle fan, which is not as popularly used. Triangle fan is very much like the triangle strip, just the order in which you draw things will be different. So a triangle fan will start from one vertex, and then second vertex and third vertex will form a triangle, and next vertex will form a triangle with the first and the last two. So a triangle fan will use the very first vertex for all of the triangles, and the last two vertices will be the remaining vertices of each triangle. So it will basically form a fan of triangles around the vertex. That's why it's called triangle fan. So you have one vertex and you add vertices around it, you just form a fan like this. It's very much the same idea. It's not as useful because you're sort of going around one vertex, and strips can be much longer than a triangle fan, so strips are a lot more useful because of that. But same idea. So you could use GL draw arrays and draw each individual triangle, or you can draw triangle strips or a triangle fan. Or we said we could use elements, right? But we could use elements for all of these. The same idea appears. Now I have a list of vertex attributes, and I'm forming a triangle strip or a triangle fan by placing my indices in that particular order, right? So I just place the index of the next vertex, and that's forming a triangle, and the next vertex is forming the next triangle. So the same trick applies to all of this. So if you're wondering what is the most efficient way of rendering a bunch of triangles, rendering a triangular mesh, that would be using GL draw elements with a triangle strip. So that would be the most efficient way. But that would require you to, you need to process your data such that a single index will be the same index for all of the vertex attributes. So if I have multiple vertex attributes, and oftentimes I will have multiple vertex attributes, the same index will represent all of those, will be valid for all of those attributes. So I'm not using a different index for surface normal and different index for vertex position. So I need to do that processing so that I can use elements. And then I need to form strips. From all this triangle data, I need to generate a bunch of strips. And they could be separate strips. I can connect them using the trick that I just showed you on the board. But if you do that, if you do all that pre-processing, you get the most efficient way of rendering your triangular meshes. So you can optimize the vertex processing part of your GPU rendering pipeline if you do that pre-processing. Now, out of all this, for the upcoming project, if you're not sure about what to do, like I told you about all these possible ways of rendering triangles, if you find yourself a little confused and unsure about what to do for the upcoming project and the following projects, I would say do this. Yeah, this is the easiest one. GL draw arrays, GL triangles. Now, this is the easiest one, but this doesn't mean that it's just gonna work without you doing any work. You're gonna have to do some work still. You're still gonna have to take a look at each triangle and copy its vertex attributes to all of the vertex attribute arrays. Okay, you kind of need to form those arrays and then send those arrays as your vertex buffer object data to your GPU. You can just take an OBJ file data and then send it to your GPU and say, oh, here's my OBJ file, render it. It doesn't work that way. Even this requires some amount of pre-processing before you can render. Okay? All right, I'm going to end it here then. Next time, I'm going to talk about shading, phone shading, blink shading, and all that stuff. All right, good. I'll see you all next time. And till then, stay safe. Bye.